everybody. I'd like to present to you AdaptivePerf today, which I already briefly touched at the last General Assembly meeting, but now AdaptivePerf has developed a lot since that time. So let me begin by basically telling you what AdaptivePerf actually is. So it's an open source code profiler designed for Linux systems, which is based on perf with our own custom patches, which I will explain later in this presentation what they are about. And it's a profiler which samples both on CPU and off CPU activity compared to original perf. And it traces every spawned thread and process of a profiled program, so that you can get a thread tree, as you can see on the right. Just to be sure, can you see my cursor?
Yes, I can see it. Yeah.
Okay. And AdaptivePerf essentially fixes the common problem with perf when which is broken stacks. At least for programs compiled with frame pointers. And this is done by detecting inappropriate kernel and CPU configurations automatically and warning the user of any issues which may arise from this. And AdaptivePerf produces, as a profiling result, interactive flame graphs and charts. So these are basically non-time ordered flame graphs and time ordered flame graphs, viewable in a web browser. And the main functionality of the profiler is designed with hardware portability in mind. So AdaptivePerf relies on kernel-based performance counters. So it should work on every computer architecture where Linux perf can run. But of course, if you want to profile more intricate interactions with hardware, other sampling-based perf events are also supported, like instructions retired or branch misses, etc. And in case of computers with weaker configurations like Raspberry Pi, it is possible to do TCP streaming of profiling data in real time to a separate, stronger machine for real-time processing, so that you have a weaker machine where you profile a program and a stronger, for example, HPC center where you can do all the post-processing basically as soon as first profiling results arrive during profiling. And you may wonder how AdaptivePerf works under the hood. So I think this diagram explains it in a nice way. So firstly, we have a command line tool, AdaptivePerf, which you run for profiling a specific command. And as soon as you run it, it configures and runs perf and instruments it through its Python API with AdaptivePerf specific Python scripts. And by doing this, perf communicates events in real time by sending TCP messages to a server called AdaptivePerf server, which is another program written in C++ where all post-processing is done. And this post-processing basically generates files for the third part of AdaptivePerf called AdaptivePerf HTML, which is a web server producing this website. I will do a live demo in just a second, so that you will be able to see it in a much more detail, I believe. And there's also a planned extension of AdaptivePerf to heterogeneous architectures. So in the future, AdaptivePerf may also run other profilers and instruct them to communicate events to AdaptivePerf server. But this is not yet available in the current version of AdaptivePerf. So the good news is that AdaptivePerf is already available for download on our GitHub. The link is here. But please know that it's still in early beta and under active development. So bugs are to be expected, and essentially all feedback, comments, etc. are really welcome, because they will help us make AdaptivePerf the best, basically the best product possible, let's say. And so when it comes to the repository structure, there are three parts. So the first repository is called AdaptivePerf, and it's the command line profiling tool and server. So this command line tool and AdaptivePerf server. And these are licensed under GPL version 2 only because of using GPL v2 licensed perf under the hood. Another repository is AdaptivePerf HTML. So it's this. And this is the web server for displaying profiling results as an interactive website. And this is licensed under a slightly different license, which is GPL version 3. And the third repository, temporarily stored on GitLab because of its size, is the Linux kernel source tree with our own patched perf. And this is licensed essentially on the same terms as the vanilla Linux kernel. And just as a quick start guide to AdaptivePerf, firstly, you need to install AdaptivePerf and AdaptivePerf HTML according to the instructions we have on GitHub, and the links are also here. I will also upload the slides after the presentation so that you can check these links out. And while installing these tools, you need to pay close attention there to the kernel settings and information about non-uniform memory access, NUMA in short. And after the installation, you need to just run this command, AdaptivePerf, and command to be profiled in quotes. And the quotes are really important here, especially when your command has spaces, because otherwise AdaptivePerf will not be able to parse that command correctly. And after running AdaptivePerf, you just need to wait until it finishes its execution and produces the results directory. And afterwards, you should go to AdaptivePerf HTML, and you can do it by firstly setting this environment variable to the path to the results directory produced by AdaptivePerf, and then you need to run Flask and point it to AdaptivePerf HTML here. And afterwards, you just need to open the website in your web browser, and you are free to browse the profiling results. So now let me just go to a short live demo of AdaptivePerf. So I'm currently, let me just zoom this in. And so I'm currently logged into to a bare metal machine with non-uniform memory access. And if I remember correctly, it has 32 cores and over 100. If I remember correctly, it was about 180 gigabytes of RAM. So the main entry point of AdaptivePerf is a command line tool called AdaptivePerf. So let me just quickly open the help message of this. So the most basic usage is just AdaptivePerf and command to be profiled. It's important. So if your command doesn't have spaces, it's not strictly necessary to put quotes, but in case of spaces like here, you must put quotes. And there are multiple options made for customizing profiling done by AdaptivePerf. So, for example, the example options are setting the sampling frequency per second for on CPU profiling, sampling frequency per second for off CPU profiling. Also, how many threads isolated from profiled command you want to use for perf itself and post-processing. So essentially, AdaptivePerf tries its best, depending obviously on the machine you run it on, to isolate the profiled command from the profilers themselves and post-processing. So the profiler and post-processing stuff basically run on separate cores, on separate CPU cores. And there are also some other options you can use. For example, so you can open AdaptivePerf server and on a separate machine, and then run AdaptivePerf with this option to delegate post-processing to that AdaptivePerf server instance running on a separate machine. Also, one very useful option is this option, event, which you can use basically to tell AdaptivePerf to use not only wall time for processing, but also other sampling-based perf events. But but available perf events is very architecture dependent. You need to run perf list to check that list before using this option. Okay, so yeah, that was a quick introduction to AdaptivePerf help message. Let me just now run quickly profile something. So just let me check if I have. Okay, let me just delete the previous results directory, and let me profile the ls command. So as you run AdaptivePerf, you get basically, yeah, you get the GPL notice at the beginning, and then you can see basically what's going on at each stage of AdaptivePerf execution. So at the first stage, the kernel settings are checked, whether everything is good. The machine is already configured, so everything here is good. But you get a warning that stacks with more than 1024 entries will be broken in your results because there's a kernel setting called perf event max stack, which limits the number of stack entries that are saved for profiling. But if you want to change that option, you just need AdaptivePerf just suggests to run this command, and afterwards you can, for example, profile programs with more than 1024 entries, because I know there are programs with producing such deep stacks. But there's also one caveat that for off-CPU profiling, currently values larger than 1024 are currently not supported. And also the CPU specification is checked, so this is mostly checking if the number of cores is correct, so that proper isolation can happen between the profiled command and the profilers. Then non-uniform memory access is checked, settings are checked. So essentially, if you have NUMA, you need to either disable NUMA rebalancing mechanism in Linux, or run AdaptivePerf on a single NUMA node for both CPU and memory. Otherwise, the rebalancing mechanism will cause stacks to be randomly broken, and this is something which we definitely don't want. And afterwards, the rest is just preparing the directory, doing the profiling itself, executing the code, and processing results. And after running the profiling, we can check the results directory. And you can see that this directory has been produced. This essentially indicates the date and time of running the profiling, the host name of the machine where profiling was run, and the command that was profiled. And the structure of this folder is as follows. You have out and process directories. In out you have mostly, usually either all of these files here or most of the files here are standard error and standard output logs from profilers and the profiled command itself. And in process you have usually either all or nearly all information needed for analyzing the profiling results afterwards, usually using AdaptivePerf HTML. So these JSON files basically describe flame graphs per thread/process. We have also some metadata stack traces spawning specific threads or processes, and we have also some call chain dictionary, which is more about internal implementation of AdaptivePerf, which I will not discuss at this talk. And now let me just go to the website where we can check the profiling results. So the results I'm showing you here are not the results produced here, because my current setup requires moving the results between machines, and we don't have time for this right now. So in the meantime, before this presentation, I profiled a sample snippet in CERN root, which uses Python and also JIT C++ code. And what you can see here is the timeline view, and the thread tree, which you can expand or collapse as you want. And for each thread or process, you have the process name, the PID, and the TID. And then you have the block indicating for how long that thread or process exactly ran for. And this is measured exactly by measuring the time between relevant enter and exit syscalls in Linux. And the block itself consists of either red or blue parts. Red parts correspond to on CPU activity, so basically doing active stuff on CPU. And blue parts indicate off CPU activity. So off CPU is essentially everything which takes that thread or process off CPU. So being blocked, waiting for another thread, or waiting for I/O, or doing calculations on some different peripheral like a GPU. All of this is counted for as off CPU activity. And obviously this timeline can be zoomed out, zoomed in as you wish, so that you can see in more detail the on CPU and off CPU activity on the timeline itself. Of course, not every off CPU activity will be shown here because of the sampling nature of AdaptivePerf. But if you want to see more details, off CPU details, you can simply just increase the off CPU frequency for profiling, but this comes at the expense of a larger profiling overhead. You can also check the specific runtime as a number of a thread or process, along with its sampled runtime as sampled by perf, by right-clicking the thread or process you are interested in. So, for example, for this thread, you can see that the runtime is 190,510 milliseconds point something. And the sample time is 158,697 point something milliseconds. And you can also check which stack trace, what stack trace in the parent thread spawned this specific thread or process. So we can see that in this case, this is the stack trace which created this thread, and this stack trace is it originates from the tutorial.sh process. And last but not least, flame graphs. So if you want to open a flame graph, you just need to double click the thread or process you are interested in. So let me just quickly grab some thread or process which is not too complex. So here's an example flame graph you have. You may see that there's some symbol names are not decoded here. It's because of an already identified issue with streaming symbols in real time from perf symbol maps, and this will be fixed. Soon. But other than this, you can see a nice on and off CPU flame graph. So this is a non-time ordered flame graph, and you can see that the blue parts correspond to off CPU activity. And hot parts, so yellowish, reddish ones, correspond to on CPU activity. And this is an interactive flame graph, so you can zoom in here or here to see to check the details of which function took how much time to process. As you hover your cursor over a specific block, you can check how many samples the specific function took. So in case of wall time, this is in nanoseconds. Obviously, these are approximate numbers because of sampling. And also what you can do is you can do interactive search. So you can type in any search query you like, and the search happens as you start typing. And you can also do regular expressions inside. So if I, for example, start typing that I want to search to find everything which starts with either TBB or STD, I just need to type in the specific regex, and you can see that essentially the search happens in real time, and the blocks which have been found are highlighted here so that you can check them out in more detail, as you can see. It is also possible to do, obviously, as I said, it is possible to also do different perf events. So in this case, I profiled page faults. And you can see we can now have a different flame graph, which corresponds to page faults now. And you can basically do the same thing as with wall time plane graphs. So you can zoom in, you can zoom out, you can do search. So you can, for example, you can look for this streamer info actions, so that you have the highlighted blocks here. And again, you may see that, for example, some names here are not demangled properly. This is also an already identified issue of streaming symbols from perf symbol maps, and this will be fixed. So, and it is also possible to do, and it's also possible to switch to time-ordered flame graphs, but time-ordered flame graphs are usually more complex on average than non-time ordered flame graphs. So at the moment, it may take some time for these flame graphs to be rendered, because these are rendered under the hood in JavaScript. We will work on speeding this up, so that you can explore all flame graphs, both time ordered and non-time ordered, and basically in a quick enough way. So yeah, so I can see here that probably this specific time ordered flame graph is at the moment, it's at the moment too complex. But yeah, let me just stop this. So yeah, this is one of the things which we will definitely work on in the near future. And you can also see that some threads or processes are marked as red. So basically, this means that the difference between the sampled and the exact runtime is significant. So that you can already know that flame graphs for this specific thread or process are not going to be accurate. And as you open the flame graph of that red thread or process, you will also get a warning message saying that the difference is too large. So let me just quickly close this, because I must have opened a too complex time-ordered flame graph. And let me just go quickly to some here we are, to some screenshots here showing basically what the warning message looks like. So you have the difference between the exact and sampled runtime is this and this percent, which exceeds, in this case, 50%. But it is possible to set a threshold to a different value, and you can set it when running the AdaptivePerf HTML web server. And yes, so that's pretty much it when it comes to the demo itself. So let me go back to the presentation. So I also want to mention a few things which have changed since last time when I presented the profiling tool back in September. So first of all, because perf and the Linux kernel internals are very closely tied together, and because it's advantageous to have everything compiled with absolutely everything compiled with frame pointers, so with the no omit frame pointer and similar compiler flags, we use Gen 2 based virtual machines instead of Docker containers, and we also provide ready to use x86 QCOW2 images, which you can use for deployment to either virtual machines or bare metal machines, in order basically for you to prepare your hardware for using AdaptivePerf in as easily as possible. We may also provide virtual machine images for other architectures in the future. And also, since last time, we have replaced embedded SVGs produced by Brendan Gregg's tools by graphs rendered in JavaScript by D3 Flame Graph library. So by doing this, we have more customization opportunities under the hood, and it also significantly simplifies the legal situation involving the usage of GPL v2 licensed perf. Yeah, it's I don't want to go deep into this legal situation in this talk, but in very short, the Brendan Gregg's tools are licensed under a GPL incompatible license. So this is why we had to change the tools. But the maintenance status of D3 Flame Graph is at the moment being verified because the last commit to its main branch was long time ago in 2022. So we may have to start maintaining this library ourselves, at least when it comes to very basic stuff, such as fixing security vulnerabilities. And obviously, AdaptivePerf is not the first profiler on the market. So I created this small comparison table between AdaptivePerf and other similar and maintained profilers for Linux. So in this case, I compared these features. So hardware vendor portability, software hardware interaction profiling, low profiling overhead, open source, being open source, of CPU profiling availability, and heterogeneous architecture support. And you can see that AdaptivePerf is hardware vendor portable thanks to using kernel-based performance counters. It can profile software-hardware interaction as if supported by a user's hardware architecture. It has low profiling overhead. It's open source. It supports off CPU profiling, and it will at least to some extent support heterogeneous architectures in the future. So compared to other profilers like Original Perf, Intel Vitium Profiler, AMD UProf, Valgrind, GProf, GPerf Tools by Google, or NVIDIA profilers, this is currently AdaptivePerf is on track to being the most feature-rich low overhead profiler amongst the most popular choices for Linux. And I want to touch briefly on future plans for AdaptivePerf. So obviously, we want to use AdaptivePerf for profiling the SYCLDB benchmark for the SYCLOPS project. So yeah, we are already in touch with Raja on this. We also want to collaborate with Codasip and INESC, and yeah, it's a shame that there are no INESC people currently at the meeting, but I will talk about it anyway. So we want to collaborate with these two companies and institutions to put AdaptivePerf in a, let's say, wider software hardware co-design context. And this initiative was already started back in September during the GA meeting, and we already have access to Codasip Studio, and we hope to be able to investigate roofline modeling soon. And obviously, I want to apologize for the lack of contact earlier regarding this collaboration, because we had to get AdaptivePerf to the state where such collaboration is practically possible, and this is happening only now. So again, my apologies for this. And another point is profiling heterogeneous architectures, so a wide range of heterogeneous architectures in a maximally open source way. It's going to be a challenging task, but we want to try. We want to try our best here. RISC-V is already in progress thanks to the access given by Raja to the Milk V Pioneer. So thank you again, Raja, for this. And also, as mentioned in the live demo, we want to speed up flame graph rendering, because some flame graphs can be really complex and they can have a large amount of blocks, and the rendering can be both time and work consuming. And this is actually the case. This is the case for JavaScript rendered flame graphs, but this was also the case for flame graphs produced by the Brendan Gregg's tools originally, because because during profiling, when the SVGs were produced, we had to wait some time for the more complex SVGs to be produced, and then when these SVGs were displayed, basically they also took a toll on computer resources. So basically, we want to work on speeding this up significantly. One of our ideas is dropping insignificant flame graph blocks without affecting the size of other blocks. So for example, if we have a block which takes less than 5%, some other arbitrary percentage of all samples, we would just not render it. So that if you have a lots of very narrow blocks, this would be not rendered, and this should save precious computing resources. But we are also open to any other suggestions if you have any. This point, very briefly, very quickly, automated tests. This was set up already at the end of last year, but AdaptivePerf has been largely redesigned recently, so we need to update the tests now. We also want to make AdaptivePerf match non-sampling based metrics such as power consumption, I/O bus usage, network bandwidth, etc. to code segments so that you can have also flame graphs or some plots over flame graphs related to this. And a student intern is coming to CERN this summer for about 9 weeks to work on the specific project. So this is one of the points which we will definitely be working on. We may also try decreasing profiling overhead even more, for example, by replacing Perf's Python API with its C, C++, Rust, or other compiled language equivalent. But because Perf out of the box supports only Python and Perl for its API, this may require another set of Perf patches from our side. We also want to try to remove or at least weaken the frame pointer compilation requirement, which might be an obstacle, for example, in case of profiling applications using closed source libraries like CUDA ones. But it's worth pointing out that full removal of that requirement may actually be unnecessary because more and more Linux distributions have started including flame pointers by default in their packages. So there is this very recent Brendan Gregg's post on his blog discussing this essentially. So in Gentoo you can have frame pointers already because you can just configure it to compile everything with frame pointers. Fedora 38 Plus has frame pointers. Recent versions of Arch Linux have frame pointers, and Ubuntu 24.04 Plus will also have frame pointers by default. So yeah, so the full removal may actually be unnecessary in this case. And we are open to any other suggestions and feedback, of course, because it will be the users who will shape the future of AdaptivePerf. And yeah, that's it. That's it from me. Thank you very much for your attention, and I'm open to any questions or comments you have.